Okay, there are two basic ways of connecting up electrical components. We can either connect them up in series or in parallel. So the goal of this segment is to distinguish between series and parallel, what those words mean, and to talk about what that means for resistors in a circuit. So in a series circuit, all of the current that goes through the first light bulb also goes through the second. Conservation of current tells us that. However, in a parallel circuit, the current has to split. None of the current that goes through this bulb goes through this bulb. The current splits. And so we say that two light bulbs are in series if there is no junction in between. So we see no junction between the light bulbs. However, between here and here, clearly a junction. Whether we take this path or this path, there is a junction in between those. Therefore, these are not in series. These are in series. We'll get to a good definition of what parallel means here in a little bit. For now, we'll say two elements are in series if all of the current that goes through one also goes through the other. Here we see a schematic representation of a circuit with two series resistors. Because all of the current goes through this resistor, also goes through this resistor, that makes them in series. There is no junction in between. They share the same current. In fact, the current is the same for the battery in either of the resistances and also for each of the wires. Conservation of current tells us that. Now, it turns out we could replace these two resistors here with a single resistor that has the exact same resistance, and the circuit will behave identically, whether it has the two original or the one equivalent. And it turns out that we can replace it with an equivalent resistance that simply is the sum of the two individual resistances. So this circuit will behave exactly the same as this circuit as long as this resistor here has a value that is equal to the sum of these two resistances. We call that the equivalent resistance. And maybe you're wondering, why would I want to do that? Well, I mean, the short answer is maybe you have a 2 ohm resistor and a 3 ohm resistor, and what you are really dreaming of having is a 5 ohm resistor. That's the simple version. But also there's all kinds of situations where you might need two resistors for a certain reason, but you need the total resistance of the whole thing to be some certain value. So even though maybe at this point we don't have enough experience with circuits to see why we care, it is something that we need to understand if we're going to understand more complicated circuits like a toaster or a guitar amp. So that was for just two individual resistances, but in general we can extend this. If we've got 10 individual resistances, man, we just add them all up. So the equivalent resistance of some number of series resistors is simply the sum of all of them. Now we can use this to help us sort of understand some basic circuits. Here's a couple of straightforward circuits. Here's a battery and one light bulb, and a battery and two light bulbs in series. If all of the light bulbs and all of the batteries are identical, how do the brightnesses compare? Why don't you pause the video and ponder which light bulb, if any, is brightest? If all of these light bulbs are identical, then this circuit has twice the resistance that this circuit has. Why? Because we could replace these two individual resistors with a single resistor that had twice the resistance of any of these light bulbs. So this circuit has a greater resistance, therefore a smaller current. Greater resistance, same voltage, smaller current. Therefore, with a smaller current, B and C will be dimmer than A. So A is brighter. How about B and C? Well, conservation of current tells us that B and C must be the same. They have the same current through them. They have the same resistance, therefore they have the same brightness. B and C are the same. So B and C are equally bright, and A is the brightest. What about parallel resistors? Here we see a parallel circuit, and what makes these parallel? They're parallel because they have the same potential across them. Now, remember that the potential across an ideal wire does not change. These have the same potential across them. That's what makes them in parallel. Let's just imagine that, let's give a value for this EMF. Let's say it's a 9-volt battery. So where in the circuit is 9 volts? Well, remember that there is no voltage drop across an ideal wire. So that means the top of my battery is at 9 volts, and everything that is connected to the top of my battery with an ideal wire is also at 9 volts. That means that it's 9 volts everywhere in yellow here. Everywhere in yellow is 9 volts. The bottom side of my battery is 0 volts. That means everything connected to the bottom side of my battery with an ideal wire is also at 0 volts. So we are at 0 volts here, 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 everywhere in orange here is at 0 volts. So this is 0 volts, this is 9 volts. Now, hopefully we can see from that parallel elements have the same potential across them. Because for each of these resistors, we have 9 volts at the top and 0 volts at the bottom. That means delta V for each resistor is 9 volts. That is the true test of whether or not something is in parallel. If two elements are in series, they always have the same current. If two elements are in parallel, they always have the same potential across them. So these are parallel elements. Now, it turns out that the junction rule tells us that the current out of the battery has to split. Some of it goes through this resistor and some of it goes through this resistor. It won't necessarily be an equal split if these resistances are not equal. We'd have to maybe do some analysis to figure out what that was. But the point is the current splits. These do not see the same current. And so our relationship gets a little bit trickier. But we still can replace these two resistors with one equivalent resistor. But in order to add them, we have to do it fancy. They add reciprocally. So I say that that series resistors add regular and parallel resistors add fancy. So we need to add them reciprocally. We take 1 over the first, 1 over the second, however many we have, and then we take the negative 1 of that, which essentially flips it over. Right? Okay. So now let's look at this situation. How does the brightness of bulb B compare to bulb A? Why don't you pause the video and consider that? Well, let's compare these. Let's see. We have identical batteries, so same EMF. So I don't know, let's say that's 9 volts. Let's say this is a 9-volt battery. Then bulb A has 9 volts across it. Bulb B has 9 volts across it. And bulb C also has 9 volts across it. So I think the brightness of bulb B is the same as the brightness of bulb A. Each bulb is connected to the same potential difference, so they have the same brightness. Now, other things are different. In this case, the battery has to provide twice the current and twice the power. Okay, here's a quick example. What things about the resistors in this circuit are the same for all three? Pause the video and consider it. I'll see you on the other side. Okay, so here we see 3 resistors. Do they have the same resistance? Certainly not. Do they have the same current? Well, the current has to split when it goes across this junction. So they definitely don't have the same current. Well, maybe we should come back to that one. Do they have the same potential difference? And they do, right? Because the top sides are all connected with ideal wires to the plus side of the battery. The negative sides all to the negative side of the battery. Bottom sides all to the negative side of the battery. Which means they all have the same potential across them. So definitely B is true. Could they have the same current? Well, remember that the current is driven by the potential and moderated by the resistance. So here we see same potential, different resistances. These will all have different currents. So the only thing that's the same here is the potential difference. How about this one? Which resistor dissipates more power? I urge you not to guess. I urge you to look at the equations and try and figure this out. I'll see you on the other side. Welcome back. Let's look at this. We're going to want to look at the power dissipated equation. Much like we did before, we want to try and find the version of this that has one thing that's the same between the two resistors and one thing that is varying. So let's go through here. I and V. Well, We know that they both have the same potential across them, but they have different currents, and without doing a little math, I can't compare those currents immediately. Let's skip that one. Yeah, again, without knowing the current, I would have to do an intermediary step to compare the currents. I can jump to this one and answer the question right away. They each have the same potential across them. Therefore, the one with the smaller resistance dissipates the more power. In fact, it dissipates 9 times as much power as the 9 ohm resistor. This one is often surprising to students. A lot of students just say, oh, well, it has to be the 9. Greater resistance, greater power dissipated. It's not quite that straightforward, right? Because power depends on current. And the greater the current is, and the greater the resistance is, the smaller the current is. So we actually could have, I kind of fudged this a little bit. We could have stopped here, right? They do both have the same potential across them. Which one has the greater current? Well, clearly the smaller resistance has the greater current. So we get the same result even if we look at this first one. We did have to do that intermediary step of smaller resistance, greater current. So it is just a little bit tricky, and it really takes some practice to be able to intuitively sort of wrap your brain around this without just having to do the math. So I'd urge you to look at the equations, and even if it seems like a conceptual question, let the equations be the boss. Here's another one. What is the equivalent resistance between A and B in the circuit? Is it 5, 10, 15, 20 ohms? It's not, I don't know, but you can pick that if you want. Okay, the first question is, are these in series or parallel? And do they have the same potential across them? No, they don't. So they can't be in parallel. Is there a junction in between them? No. Would they have the same current if I hooked them up to a battery? Yes, they would. These are definitely in series, and so we know that R equivalent is equal to R1 plus R2. We simply add these two. The equivalent resistance is twice the individual resistances. So that's something to kind of keep in your back pocket, and remember, if you have two resistors that are identical and they're in series, then the equivalent resistance is twice either of the individual resistances. In other words, and we can make this a more general statement, that when you put resistances in series, the equivalent resistance is always greater than either of the individual resistances. Here's the parallel version. What is the equivalent resistance between A and B in the circuit? I'll erase this so it doesn't trick you. Why don't you consider that, and I'll see you on the other side. Now, is there a junction between these? You bet there is right here. If I hooked them up to the battery, would they have the same potential? Yes, they would. Therefore, these are definitely in parallel, not in series. So we should use this equation here. And if we just run our calculator real quick, we find that this is 5 ohms. So this is often a little bit of a surprising result for students. Also, notice that the equivalent resistance of two parallel resistors is smaller than either of the individual resistances. And again, if we're just talking about two identical resistors, the equivalent resistance is always half. The equivalent resistance of two identical resistors in parallel is always half of the individual resistances. Well, here's another example. What is the battery current here? I'll go ahead and erase my board. I'll see you on the other side. Why don't you try this one? Okay, we could use the loop rule for this. A couple of different ways to approach this, but I'm going to use the idea of equivalent resistance instead. We see that the equivalent resistance here is 12 ohms plus 6 ohms because they are in series, right? So we have an equivalent resistance of 18 ohms. We know that I equals delta V over R. We get a new piece of chalk. And so we should have 12 volts divided by 18 ohms gives us 2/3 of an amp. Okay. Okay, so equivalent resistance is 18. Again, I already stated this, but the equivalent resistance of two resistors in series is always greater than the individual resistances. How about this one? What is the current in this battery? Figure it out. I'll see you on the other side. Okay, what's different now is that our resistors are in parallel. So do we expect a greater current or a lower current? Same battery, same resistances as this previous problem. Well, I think that the equivalent resistance of a parallel circuit will be less than of the series circuit made of the same elements. So I expect a greater current. This is our equation for the equivalent resistance of parallel components. And so we're going to crank through this. This is 1 over 12 ohms plus 1 over 6 ohms to the -1. And we get 4 ohms. Now we can do Ohm's law. I equals 12 volts divided by 4 ohms. 3 amps. Indeed, we get a much greater current, don't we? Okay, so the equivalent resistance of a parallel circuit is lower. Lower resistance, same voltage, greater current. Not too bad. There's some tricky things here. And I think that a lot of people think, well, more resistors is just more resistance. Not always. It really depends on how you hook them up. Here's another example to help us kind of wrap our brain around that. So initially we've got the switch open, and we've got this current going here in the left side of my circuit. What happens to the current in the battery when I close the switch? Does it increase, stay the same, or decrease? Why don't you try and figure it out, and I'll see you on the other side. Well, I think the way to approach this is from Ohm's law. So when I close the circuit, or close the switch, open the switch, delta V stays the same. It doesn't change, right? That's still the voltage put out by the battery, the EMF put out by the battery. It's what's driving the current. What does change is the resistance, right? So does the resistance increase or decrease when I close that switch? And by the resistance, I mean the equivalent resistance of the entire circuit. And indeed, adding a resistor in parallel decreases the overall resistance of the circuit. So we have a lower resistance, same voltage, we should have a greater current because the equivalent resistance decreases and the potential difference is not changed.